Well, actually good afternoon. It's been wonderful to arrive here last night and get up this morning and have such a cool blast of air to wake me up. California isn't quite as cold as this, although I live in Northern California, so it's almost as cold as this, but not quite. Today I want to talk, as Roman's just mentioned, about the relationship between classroom assessment and large-scale assessment. And I want to point out that I'm going to go the opposite way to the way it's usually done. Usually people think, oh, well, there's that large-scale assessment, PISA, TIMS, all those things with initials, and we better do what they tell us to do. And I actually want to turn that around and say, well, we better figure out what we do in the classroom and do that well, and then tell them how to do it. And I think they'll listen if we tell them and if we have a way to tell them. And the problem at the moment is it's hard to articulate between the two. What a teacher does every day in the classroom is a very micro version of the very large-scale thing, the very coarse-grained thing that is done in large-scale assessment. And so it's hard to see how those two things work together, although indeed there is a strong relationship, as Roman pointed out. So I'm going to basically talk about three things. I'm going to talk about what I see as the problem we currently have between classroom and large-scale assessment. I'm going to introduce an idea called learning progressions, which I think is a way to articulate the relationship between them that's better than the problematic relationship. And finally, I'm going to then have a three-part strategy to actually make that happen. I like things in threes mainly, so there's lots of threes throughout this. So this is the first part. What is the current problem? Now, this is taking an international perspective. Basically, this is what I'm going to talk about now is going on almost everywhere that large-scale assessment is taking place, everywhere that PISA is being used, or TIMS, or any of the IEA tests. This is the sort of problem that I'm going to be talking about here. It looks different in different countries. I'm not familiar with your particular situation here in Poland. I mainly know situations in the US, UK, Canada, Australia, mainly in English-speaking countries actually. So let's have a few definitions to start with. It's an academic talk, we always need our definitions. Let's talk about this idea of formative assessment. Of course, that's what formative assessment is, what's supposed to go on in the classroom. Assessment to improve. This is actually a definition by my colleague Paul Black. An assessment activity is formative if it can help learning by providing information to be used as feedback by teachers and by their students. So it's not just for teachers, but it's for the students themselves, of course, if the students are old enough. It doesn't work with little kids, but with older kids it works. In assessing themselves and each other to modify the teaching and learning activities in which they are engaged. Notice it doesn't talk about, does it use books, does it use films, is it in lectures, is it in workshops? That's not what matters. What matters is the purpose. What makes it formative is the fact we're going to use it to change how we do our next piece of learning. That's the essential thing. Now let's contrast that with this other idea of summative assessment. And of course, summative assessment is what large-scale assessment is supposed to be. So let's see what that is. An assessment activity is summative insofar as it is being used to provide a summary of what a student knows, understands or can do, and not, notice the negative, to help by providing feedback to modify the teaching and learning activities in which the student is engaged. So in a sense, this is everything else. This is if we're not going to actually help, we're just going to say, that's where they got to. That's where they are at the end of the year. That's where they are when we gave this test. That's summative. Summative goes with large scale, formative goes with classroom assessment. Again, notice it doesn't say that they're tests, doesn't say exactly what they are, it's the purpose that distinguishes these two things. And notice also that it doesn't say that you couldn't be doing it for both reasons. That is, of course, the teacher could be giving a summative assessment at the end of the year, and they could use that information to give summative results to the students in the class. But the teacher could also look at that summative information and say, gee, what did they learn? Are there any things that no one seemed to learn that I wanted them to learn? And of course, then plan to change their instruction for the following year. And that would be a formative use of that summative test. So notice the two can actually coexist. It's not that they're always apart. And indeed, many people will say, well, let's try and use PISA, or let's try and use TIMS in a formative way. And there are some uses for that. So, but I think we need to be clear on these two purposes. So, first of all, formative assessment, it's providing feedback. Summative assessment, it's providing a summary of what they know, but not providing feedback. That's this essential distinction. So, with that definition in mind, now I can talk about the problem that I started talking about. The problem is that there are the effects of summative, and here I think of state or national testing or regional testing. Could be, could be school testing also, of tests on curriculum instruction in the classroom. How does that work? Well, here's a picture that you'll see often in educational sort of settings. I don't know who invented it. It's called the CIA diagram in the US for curriculum instruction and assessment. But in the UK they call it the CPA diagram, because here they put pedagogy instead of instruction. That's just a little detail. If you're reading about this, you'll see them differently. But how it's meant to work is like this. That the idea is we design our curriculum. On the basis of our curriculum, that's a statement of knowledge or skills the student's supposed to have. We then design our instruction. We carry out our instruction. We test the instruction using our assessments. Of course, they're designed to match the instruction. And then, finally, there's another feedback where we say, well, did they learn it? That's the question. This arrow here is essentially a question. Did it happen like I expected it to? And, of course, that means it's a cycle, because the answer might be yes, in which case we go on to the next thing, or the answer might be no, in which case we say, oh, well, we better redo it. We start over here, we rethink it, and we go around this cycle again. So it's a cycle of learning, it's called. And this is sort of a traditional way that people in education explain what they're doing. Well, the problem is that the way large-scale testing works is sort of doesn't really work this way. And here's a picture that a colleague of mine, Paul Black, from King's College in London, designed. He calls this the vicious triangle. Not the triangle of learning, but the vicious triangle. And what he says is what happens here is you have your idea of the curriculum, and yeah, indeed, it's driving instruction as it should, but the curriculum is also used to create the tests. And these are the standardised tests, and these are the standards that you'll see the curriculum is written in. Creates all these little standards, and then the assessment drives the instruction equally as much, or perhaps even more, than the curriculum derives instruction. So effectively what happens is this instruction, what the teacher does, gets squeezed between here's the test and here's what they're supposed to do. And unfortunately, if those tests are being used to evaluate the teachers or their schools, then the one that's going to be the most important is this one, of course, because this is where the rewards and punishments lie. This up here, this is the ideal, we'd like that, but this is in practice perhaps the bad side. So it's the triangle, instead of being this nice, developmental cycle with all good logic of curriculum instruction, that turns into this vicious triangle. And that's the central idea that many people, including Paul, including myself, worry about these state tests. So here's some quotes from, this is from a colleague of mine, Carol Harrison, who's been interviewing teachers in the UK, where this has been going on for a long time, and there's a strong tradition of state testing. And what she says is, This is a quote from a teacher called Kate, who she interviewed. And she says, "When it becomes so whittled down to specifics, that's when it kills." You've got to get the context here. She's talking about killing her enthusiasm to teach. As a teacher, I don't mind marking. It's when you are marking in a very narrow way, where you are not allowed to make assumptions, that deadens, especially with the KS3 tests. And these KS3 tests are the acronym that go with the state tests in England, this is. You prepare them in a very specific way, and you boost them, and you give them strategies, and you program them to do things in a certain way. Then that is not the way I would naturally teach. So what Kate is talking about is what happens when the curriculum goes down here and bounces back up here. It doesn't look like natural instruction. It doesn't look like, oh, we want to teach things, so let's find the best way to teach it. It says, oh, well, there's going to be all these little things called standards. So that's one teacher talking about it. This is some information from the US, and it's from a survey that was carried out by a group called the Teachers Network about NCLB testing. Now, in the US, No Child Left Behind is NCLB. And that's the legislation that came up in the early 2000s by Bush. And it's this very strong basis of testing by standards. And this is what the teachers had to say. They thought 37% it was somewhat useful, but 42% thought it was not at all helpful. That's pretty poor support from the teachers. Encourages rote drill. Of course, this is memorization. 40% thought it did that. It eliminates the curriculum material not tested. So this is one of the issues with these state tests. They're only going to go for a certain amount of time, an hour, 2 hours, something like that. You can't test everything in 2 hours. Some things are going to be left off the test, so they get left out of the teaching too. And that's a serious problem, especially if you're using a very limited form of assessment like multiple choice items. Looking on the good side, does it encourage them to improve their teaching effectiveness? Of course, this is the NCLB legislation was supposed to be a way to encourage teachers to improve their teaching effectiveness, but only 3% of teachers think it does that. Is it an effective way to assess the quality of schools? And of course, the NCLB is not just, it's at the teacher level and at the school level, and only 1% thought it was a good way to do that. And has it contributed to teacher burnout? Now, what's teacher burnout? That's teachers resigning, saying, I can't do this anymore. I've got to go and get a job in McDonald's. Forget that. Forget teaching. And 69% thought it did contribute to teacher burnout. So the teachers are leaving, and it's usually the good teachers who leave, because they're the ones who are upset by things like eliminating the curriculum material not tested. They're the ones who don't like rote drill. The good ones are the ones who are leaving. So this is not a good story, is it? It's really quite a bad story. Now, Paul Black and myself and several others of us have started to think about this triangle. And we think that we have to modify it. For one thing, we want to put right in the middle here a theory of learning. We want to say it's not just enough to have a list of standards. I don't know if you've looked at these sort of state testing standards, but basically they're just a list of facts. Here's the facts they got to know in grade 2. Here's the facts they got to know in grade 3. Here's the facts they got to know in grade 4. And that's not a very good structure of curriculum. Really, we might not even want kids to know all that many facts. We might want them to get skills. We might want them to get competencies. So we need to have something that embodies that. And of course, I'm going to suggest that this idea of a learning progression will be our theory of learning. And then we say, yes, well, we definitely want that the curriculum is going to determine instruction. And we think that assessment has to play a different role. It really has to go both ways. Sure, we do think that it's a good idea that the assessment is informative of the instruction, but we need this sort of two-way street here and a two-way street here. And I'm not going to go into the details of that, but as I talk through the rest of the lecture, I think you'll get a feel for what I mean by that two-way street there. By the way, if you have questions feel free to ask. It helps me if I hear that you guys have questions. I may be using, jargon terms from the US or something that you guys aren't familiar with, or I might just be rushing over things. So please do feel free to ask me questions. I'd appreciate it if you do, actually. So why don't I just pause for a minute and say, have any questions so far? No questions so far? This is the easy bit. Yeah, it's true. We'll get a little more technical later, but most of this is going to be broad brushstrokes. So this is our idea. We want something, first of all, we're going to need this theory of learning, but we want to have a different view of this triangle. There's some other things that I just want to mention that are also associated with this. One is this, there's this classic criticism of US curriculum, specifically in mathematics and science, that what happens is they become a mile wide and an inch deep. That is, they tend to cover every possible topic, but only this deep. And there's sort of a curriculum politics reason for that. And that has a classic example. I don't know whether you guys have experienced this yet, but nanotechnology. Right, nanotechnology is a big topic in science. It's important. New, we should know about it. So what are we going to do? We've got to put it into the curriculum. We'd all better learn, kids have to learn about nanotechnology. You know what nanotechnology is? Sort of the science of the micro. Putting robots inside your bodies. There's one way to think of it, okay? So it's, if it works, it's going to be great. But the question then is what happens when you do that, when you put nanotechnology into the curriculum and the curriculum time doesn't increase for science and we don't take something out, then what happens to science? It gets shallower and shallower. We learn less and less about all the other things because we've got to afford time for nanotechnology. And that is actually one of the issues that goes along with this. We need to find ways to not do this. We want our school topics, our curricula, to cover the important things, but they may not cover everything. And that's a tough thing for people to say. Should we say to all those important scientists, no nanotechnology? Well, maybe we do, because we have to be able to say some things are important and the rest they'll catch up with later. One of the aspects that goes with these state tests is that sort of a principle, and this is an attempt to actually cover the curriculum, not to leave things out, is that every standard has to be tested by several items. And that's one of the things that causes the problem with curriculum coverage, because you just can't do that. So we need to find a more efficient way to test and use items. We need for the standards to be interpretable by educators and policymakers. And for instance, if you go and look at the standards for California, say, I come from California. In grade 8 science, there are 65 standards. There's 65 different things that they want students to learn. And it's very hard. Now the teachers need to know that because they're teaching them through it. But can policymakers, when I'm talking like, can the superintendent of schools and others, politicians, understand 65 statements? No, they can't. So they need a way to understand that. We also need to enable long-term views of student growth. We need to be not just looking at what we're doing in grade 8 in science. We need to be looking at what we're doing in grade 7 and grade 6 and grade 9 and think about the whole way through. So these are 4 different issues, and I'm going to suggest that when we talk about learning progressions are actually a way to address all of them. I'm not saying that they make it easy to solve them, but they are a way to address them. So there's another aspect of this problem that you see, you might not come across this if you don't deal with testing much, but I deal with it all the time. And I characterise this as the wish of large-scale national testing programs. That is, to have their results of the large-scale tests be useful diagnostically to teachers in the classroom. That is, they'd like, when you give those state tests, which we're paying a lot of money for, and we're making the kids spend hours taking, teachers should be able to use them. Now you look at it and you think, well, gee, obviously they should be able to use them. But the truth is, that most teachers, say if you're a math teacher and you've got students in your classroom, you know whether they're good students or bad students. You already know that. It's nice if the test confirms it, but in fact you know it. It's not a new idea at all to you. So that's the whole point of this word diagnostic. We need to be able to go down below that level. And that is really hard, is the problem, because there's 65 standards and we've got to have an item for each of them. And in fact, as I put it here, this is asked for by state testing directors and promised by testing companies, but indeed it doesn't really happen. So you see rather what I consider unethical solutions is that people will give raw scores for subscales. You know, they give these sort of estimated locations for the overall score and then a raw score. And the reason they do that is because they don't want to have to report the standard error. They can say, well, that student got 2 out of 5. That's a fact. But really, of course, we know that we should be considering the uncertainty of that. And for that reason, I consider it to be an unethical thing to do. There's another solution you see, and in fact this has become much more common in the US. There's a thing called the Common Core. I don't know if you guys know about that, but that's a new form of the national curriculum. And what you do is you make little copies of the state tests and regularly administer them throughout the year. And these are called benchmark tests. And there are some serious problems with this too, because if you think about it, if you've got an end of the year test, well, it's a good thing to give at the end of the year when the students have covered all the curriculum. But if you give the same test halfway through the curriculum, well, what does that mean? It means that they've only covered half the curriculum, but we've given them a test for the whole thing. And, well, they're not going to get half of it right. So it's automatic failure. So this is an oddity to do this. People are trying to do better at it, but in fact it's generally a bad idea. That's the first part. Okay, so this is the current problem as I see it in many countries, all over the world in fact, that we've got teachers in classroom teaching away, we've got these tests come in, international tests, national tests, perhaps regional tests, and they're going to be used perhaps to evaluate that teacher, or at least to evaluate their class or their school, and is causing this problem of squeezing the curriculum. So I want to talk about this idea of a learning progression. As a background to now how might we address that. So here's a definition, again another definition here, definition of a learning progression. Learning progressions are descriptions of the successively more sophisticated ways of thinking. Notice it's more sophisticated ways of thinking about an important domain of knowledge and practice. Notice that element, it's an important domain of knowledge and practice. That can follow one another as children learn about and investigate a topic over a broad span of time. So it's meant to be over a long time, at least a year, maybe several years. They are crucially dependent on instructional practices if they are to occur. This is, for those of you who are going to get the notes, do they have the overheads for this? Can they get them, download them from somewhere, Roman, if they want? Oh, well, not now necessarily, but later perhaps. Yeah, it'd be good if you could make available to people the overheads, and the last slide on the overheads actually gives these references so they can go and look them up. But this was a task force put together to study learning progressions. By the way, they're also known in other areas. This is sort of, they called this in science education, but in math education they're often called learning trajectories. Well, sometimes you also hear progressions of developmental competence and even other sort of strange terms like profile strands. So it's the same idea under different names, and different people have been inventing it. When there's a good idea, often it pops up in different places. I want to point out what this is not, though. Notice that it's not the structure of knowledge. Right? The structure of knowledge says, well, when you know all about something, say you know all about calculus, just to take an example. You know all the facts, you know all the ideas, there it is, and there's a certain structure to that knowledge. And we think, well, how will we cut up our curriculum? We'll take the bits of that structure and we'll teach them. Makes sense, right? Well, this is not that. This is the ways of thinking. This is how students start to understand calculus. That's different from the structure of knowledge. It's important to get this idea, because this is as people are going through, when they first come across calculus, what are their ideas about? If they're being taught well, in my view, many of their ideas will be pictures. It won't be the structure of the knowledge about calculus. It'll be pictures. It'll be saying, well, what's a derivative look like? What does integration mean? What does it mean to get an area under a graph? What does it mean to think about the slope of a graph? So they get the ideas first. And then later on they go on to the technical side of it. How do we write an equation for that? What's the equation for the derivative compared to the original function? And then maybe later on, when they really get further along, they want to learn the maths of it, you get those classic epsilon delta proofs, where you prove as epsilon goes to 0, the slope starts to be defined as the derivative, and so on. So this ways of thinking is something to do with the psychology of learning. It's not to do merely with the structure of the discipline. It's not that the structure of the discipline is unimportant. That's still crucial. But you've got to know also how students learn it. And the learning progression is the progression of the understanding and the thinking. So that's the crucial bit here. A couple of caveats. It's important to say that there's more than one path through any learning progression. There's often many ways. As I said, if I'm teaching something, a mathematics topic like calculus, I would teach it graphically first off. And so most students would probably start thinking graphically because I was teaching them. But someone else might do it a different way. They might say, well, I don't like graphs, I like to write equations. And so they do it with equations. So of course, there would be different paths. But we want to think of the learning progression is how they grow in sophistication to a certain point we want to get to. Second thing that comes up pretty quickly when we do this is that there's sort of a political issue here. I call it the politics of the curriculum. We need to debate what are the most important things for kids to learn. We don't, as I was saying before, I don't think we do that well at the moment. Many curricula sort of accumulate by what I call accretion. That is, we just add things on, like nanotechnology and so on. And of course the problem is that they dilute the curriculum. And one of these ideas about the learning progression is that it gives you a way to think about that. Something's important not just because I think grade 5 kids should know that. It's because when they get to grade 7 they'd better know it or they won't be able to do something that is crucial at grade 7. So we're thinking about this progression all the time. And what's important is what's foundational to what's important later. And we need to think those through. And in fact, what we need to do is to end up with fewer standards, those horrible little curriculum statements, per grade level. Now, this is once again, my colleague, Carol Harrison, has been working on this in England, and they've been trying to create these learning progressions. And here's some testimony from teachers who've been using those. The teachers she's talking about in this case were teachers of English language arts. They're teaching kids to read and write, basically, in English. Those judging, that's the English teachers, have a construct, a sense of what constitutes the relevant quality, which cannot be reduced to an explicit or atomised list. So the idea is that one's understanding of this learning progression is not just something you can write down as a simple list, because it's actually quite subtle how things relate to one another. It's important to have this clear perception of what's at the top, what's being good at English, at being good at writing. And in their case, these core characteristics that are good at English are not mechanical things like you might find in a list of standards, but they're things like creativity, flair, insight, effective expression and communication. So they're going beyond the facts to the skills and the competency. Here's from another colleague, Bronwyn Cowie, talking, these are some things that teachers had to say about this. as I had visualised where I wanted students to go and how to get there, I was more comfortable in predicting where to go and be specific in my interventions. So her curriculum planning was something that was strongly determined by this idea of where to go, of what's the broad feature of this. And here's some examples that you guys can look up. In fact, this website here was put together by a National Academies Committee that I was chair of, and it includes two quite detailed learning progressions, one in the topic of biology and evolution in biology, and the other on the topic of the molecular theory of matter, both classic science education topics. And there's also, more recently, this is forthcoming, but it was actually 2014, so it is actually out now, by Alonso and Gottwals. It was a book of papers presented at a conference called Learning Progressions in Science, and it includes about 8 or 9 of these progressions, as well as quite a few debates. There are people who say this is not a good idea, and there's some nice essays by those people in here as well. And here's an example. This is actually the example, the second one, this molecular theory of matter. And this is what we teach kids about science in middle school in the US. And it's really about, well, what does it mean that water freezes? What does it mean that water evaporates? Topics like that. And what are our physical models, our mental models we might have of that? And here's a very coarse-grained picture of what a learning progression could look like. So really at the middle here is sort of just knowledge about changes of states. Physically, what does it look like if something melts or something freezes? Or it sublimates, of course, which is pretty unusual. But as well as that, we want to then think about, well, how does the structure of molecules relate to that? And how do we then have what's called an atomic theory relate the macro evidence we might see to these models? And really this is putting that together. But of course we also need to know some things before that. The students need to know about scientific ideas of density and mass and volume and how we measure them and how we put them in graphs and so on. They need to know about statistics and what the pictures might look like. And they need to have some very basic knowledge about the properties of objects. This is very straightforward day-to-day stuff, like what happens when we boil a kettle, etc. So this starts off at a very low level, and we go up here to the sort of observations we might do in the lab. But this is important that people have these experiences that lead up through this to putting all that together in a solid story about how students come to understand the current ideas of physicists about why matter is like it is. When I talk to good science educators about this, they always say this is the most amazing thing. Why is that amazing? Why is that amazing? Anyone got any idea why it's amazing? Have a guess. Why is it amazing? What happened then? But it happens every day. So this is this point about this, that's an everyday thing, right? But when you get up here, you find out something that tells you that that's amazing. Well, the amazing thing is that is almost all empty space, and that is almost all empty space. They're both almost all empty space. And what would happen if you drop something through empty space? Just go straight through. But it doesn't. And it's an oddity. And that's one of the sort of the moments of understanding that you're trying to bring students to have by taking them through this whole process. That's a case where what they know every day is contradicted by the theory. The theory is really odd, but true, because it does stop, right? Anyway, that's I enjoy working on this. I've been working on this with, again, my colleague and friend Paul Black. And there's actually a published paper on this topic now that once again is in the reference list at the end. So that's a very quick sketch. I'm going to show you some more details later from some other ones. One thing about these progressions is that there's many aspects to them. There are many facets to the concept of a learning progression. My colleague Rich Lehrer has been pointing this out to me. He says that it must coordinate efforts across the axes of discipline, learning, instruction and assessment. So there's 4 facets. Disciplining means the discipline of the science, the structure of knowledge. Learning is what students learn, how they learn. Instruction is how do we create instruction to go with that. And assessment is how the hell do we find out whether we did it or not. So let's just quickly look at those. In fact, there are 4 progressions. One is this idea of a content progression, and that is what I started off talking about, the concepts and practices of a field of inquiry. That's the knowledge that goes with that, what we call the student knowledge progression. These are learning refers to the states of student knowledge. These 2 things, it's important to make sure you understand the distinction between those 2. Textbook writers often forget that. The textbook will follow the discipline, the structure of the discipline, but will not pay any attention to the way students actually learn it. What I'm most interested in, because my speciality is assessment, is this outcome progression. How do we see things that tell us that the students are making that progression? How do we assess them? And my colleagues who are working in the area of curriculum and instruction, they're the ones who are interested in this teaching progression. How do we change what we do as we want to foster students moving along this? So these are the 4 dimensions of that. And now I'm going to sort of revisit, I'm going to go backwards just a bit and talk about, well, how does it revisit these issues we brought up? How does it respond to that? So one is in this idea of curriculum politics. And I mentioned nanoscience. So everyone wants to add their special topic into the standards. So the strategy here is that we express the curriculum at a grain size that is manageable and debatable. So instead of thinking of the 65 standards that are in grade 5 science in California, we might think about things like this. Is it important to know all this? I'm getting one nod there. But if you're a historian, you might say, I don't care about that stuff. Because it's never mattered for history. So we have to be able to think of these sort of big things. Not think about tiny little things, but think about big things like this and say, what are the big important things? And in fact, what I would say is each subject has only just a few learning progressions each year. We concentrate on the things that are most important. And the tough thing about this is biting the bullet about teaching less so that students learn more. They learn more depth because we don't teach them so many facts. We want to go more deeply into those ideas, the big ideas. The second topic that's important here is this relationship between large-scale and classroom tests. In terms of classroom assessment, teachers need to have a guide for understanding and planning of their curriculum. And learning progressions indeed specify targets for assessment that are appropriate level for planning at the classroom level. And my solution is to have a particular way of doing this. We build what I call outcome progressions based on progress variables designed using the BEAR assessment system. And I'm going to talk about that in the last third of the lecture. So just hang on to that idea. Unfortunately, it's tough. It's really hard work. And it's a lot more work than test developers would usually expect. And it's very similar to creating a curriculum. In fact, what you essentially do is you create a generic curriculum and you make your assessment work with that. Thinking of the large scale part of this, what we soon deduce then is that the large scale assessment must not be inconsistent with classroom assessment. It must not squeeze the classroom assessment, as I talked about in that vicious triangle. And in fact, we need to start with the classroom assessments and then create the large-scale assessments as derived measures. And I'm going to illustrate exactly what I mean by that, again, in the next part of the lecture. And we will, in fact, what we'll do, we will identify these things I've called not points. Points in the curriculum that are really crucial to making further progress. And they're the things that should be in the standardised tests. Right now, we don't know what those not points are, we just know we've got lists, so we're in trouble. And the difficulty there is that this is actually something that hasn't been well researched. So there aren't a lot of learning progressions, and figuring out what the knot points on them is something that people haven't done. So that work is something that's very important to carry out. And hence, the relationship that I want to say is the important one, and should be the case, is that classroom assessments are the determinants of the large-scale assessments. That's flipping the relationship that is being imposed in many countries at the moment. In many countries it's the other way. We're going to take the PISA tests, or we're going to take the state tests. Well, we better start learning the curriculum that's behind the state tests. We better start studying the items. You'll find that there's in every country where they're using state tests, there's a marketplace of items that were used the previous year, or maybe that was somehow got out of the testing companies who are making all this, the testing institutions. There's a marketplace for such things. Because of course it does help. It'll help your kids if you can show them what the items are like and tell them what the right answers are. So, the strategy for that is organising these classroom assessments via learning progressions and derive the large-scale assessments from those learning progressions. And so the three-part solution is create progress variables. I'm going to talk about how we do that. We'll put them together in learning progressions, and then we'll take a sample from the learning progressions, and that'll give us the large-scale assessments. And so these learning progressions, in fact, create both the classroom level and the large-scale assessments. I've talked about the first two topics. There's the problem. There's this idea of a learning progression. I've talked generally about how we might use the learning progression idea to solve that problem. And now I'm going to talk about how we might actually go about that. I'm going to work through an example, a particular curriculum, and talk about how we solve the problem for that case. So it's not just theory, but in fact we can do it in practice. First of all, one construct at a time, the bare assessment system. So one thing we're going to do with our learning progression, we're going to take them one dimension at a time, basically. And I'm going to use a particular example for this. This is called the ADM project. Its full name is Assessing Data Modelling and Statistical Reasoning. The PI on the project is Rich Lehrer and Leona Schauble, and they're from Vanderbilt University in the US, and I'm working on the assessment side of that. We have teams of graduate students and postdocs working with us at both Vanderbilt and at Beer. And we've actually been doing this for 7 years now, so it's been quite a long way down the track. So we describe ourselves as a multidisciplinary collaborative where there are teachers, learning science experts and assessment experts. We have this what we call a developmental perspective on learning, and it has essentially produced a learning progression with 7 dimensions of learning. We use what's called a reformed curriculum, and it's its own special sort of thing, and this is really due to Rich Lehrer and Leona Schauble's work. But what they do is they have these whole class discussions about conjectures, and they debate and argue. They have teams of students debate and argue. Is this the right way to do it? Is that the right way to do it? Within the instruction. But also involving a lot of activity of the students actually measuring things, and I'll show you some examples of that as well as we go through. And here's a little picture that they've designed to illustrate their theory. So it's interesting, this is actually part of math in the US, data modelling, but the examples are all science. So it's a very nice example where science and math come together and really teaching both of them at the same time. So it starts off with, this is, as you can see, this is a cycle, but you have to start somewhere. So they generally start with posing questions. There's some interesting question. And often the students themselves won't come up with this. This is in middle school. They don't really care about science all that much in middle school. So the teacher tells them what the question is. And this particular, it's hard to make out this picture, but it's actually, this was a school near Vanderbilt University, and in the back, in an empty area at the back of the school, there was a swampy area. Sort of shallow pools, you know, like about this deep. And so the question was that the teacher said, well, what's growing there? What's growing in those pools that you think are just rubbishy pools? And the students actually went out and started looking at that. And so the questions were about, well, what animals live there, and how many of them are there, and what do they eat, and so on, all sorts of things like that. What eats those animals? That's the sort of question. And then, so you've got these sort of questions that are real world questions of some sort, scientifically oriented, of course. But then the next step is that you need to generate and select attributes. Okay, so what are we going to measure about these animals? Are we going to measure how long they are, how fat they are, how much they weigh, etc. All sorts of things like that. And then you actually go and measure them. Now, so we've now got measures of all these little creatures, these critters that live in the pool, and we need to think about how we're going to structure and represent the measures. And of course, what that turns into, that's when it becomes data. It becomes patterns of maybe zeros and ones, or zeros, ones, twos and threes or something. And then we have to think about how we're going to summarise the data. And that's where statistics comes in. This is where statistics meets science. And then, of course, they do something really unusual that's hardly ever done in K-12 education. They say, well, we're not just going to measure and do statistics, we're actually going to see if we can now simulate or model the answers to these interesting questions we had up here. They're actually going to create probability models of the statistics that they measure down here. And it's very, very interesting. These are middle school kids. Probability, you may know that probability is one of the hardest topics to teach. The adult population doesn't understand probability. Otherwise, they wouldn't engage in all those gambling they do. But they actually get them. They start off, I mean, we could do this with computers, but the problem is the kids don't understand what goes on inside the computer. It's meaningless to them. So they actually start off with spinners, little spinners that have, they'll have probability diagrams, and they'll spin them and simulate by hand distributions to see if they can understand how they got these distributions. What would generate distributions like what we get down here? And so they have this modelling chance, and then they go back. Then what happens is that brings up new questions. Why did it look different here from my simulation? Why did my real data look different? Etc. Now, in fact, later on, they get sick of doing all the spinners. They don't want to spin thousands of times. So they do, in fact, have a program on their laptops that has a very diagrammatic way of showing what the spinners are doing. And it's sort of, it's a little picture of the spinner spinning. So it's not just all done by hand. But it has to start off with hand experience, because otherwise kids don't understand it. There's this sort of theory of how they do that, and they have these sort of interesting questions. There's one unit that's about, looking at ponds and wastewater. Another one is looking at silk moths and the life cycle of a silk moth. Another one is much more, not so deeply scientific. A very simple activity they do is the students have to measure the arm span of the teacher. Sounds like a simple thing to do, doesn't it? But it turns out when you get groups of middle school kids to do it, they have interestingly different results. And another thing they do is they also go out and they measure the heights of tall trees. Now, the reason that these two things are interesting as measurement things is because it's hard to do it exactly. That damn teacher, he does this and he does that. He doesn't. Sometimes you measure it one way or another. And so they actually study good ways to get good measures of that. And the way they measure the heights of trees is through trigonometry. Unfortunately, math teaching isn't very good, turns out. And so they don't really teach the trigonometry. They just use a little machine that effectively uses the facts of trigonometry to give you a prediction of the height. But they're the 4 examples that they've been using in this curriculum to do this. Now, my interest in this is the assessment side of it. I mean, I think it's a fascinating curriculum and all that, and I like to work with people who do good and important work in curriculum, but I'm interested in the assessment. And so this is where assessment comes in now, because what we're going to do is talk about what I call a developmental perspective on creating assessments. And what we start off with is a thing we call a construct map. This is an idea of a unidimensional something or other that the kids get better on. Now, by the way, just as one little footnote, I'm going to be talking all the way through this of applying this to achievement testing and to cognitive dimensions. It can be applied just as easily to non-cognitive dimensions such as attitudinal scales and behavioural scales and so on. But I'm not really going to talk about that. But the structure, it turns out, is exactly the same in either case. But just for those of you who have that interest in those sort of non-cognitive variables, it works that way too. So we start off with this idea of a construct map. This is a description of the variable. In achievement testing, it'll be like, well, where do they start? Where do they go to next? Where do they go to next? And where do they get to in the end? In other words, it's a very simple version of a learning progression. We use that to start to figure out what the item should look like. How should we design the items? There's a very particular issue comes up there. Because, I mean, we all know how to make items, right? You've all taken tests. Every one of you has taken tests. You know what items look like, so you can make them up. Well, turns out that's not completely true. At least not according to this, because what the items have to do is they have to relate back to the construct map. So we need to be able to say, well, this item is tapping what part of the construction map? Is it tapping the hard bit, the middle bit, or the low bit? So there's a little bit more than we normally do. Of course, the point of the item is that it creates outcomes, and we need to be able to categorise those outcomes, and we call the system of doing that the outcome space. This is what allows us to take a range of, it could be an essay, could be a multiple choice item, responses, whatever, and we give value to them. Basically we say this is right or this is wrong if it's dichotomous. Maybe it's polytomous and it's very right, sort of right, probably wrong. The next step we need to do is, this is where we get our measurement data, comes out of this, and we need to be able to summarise it. And we're going to summarise it using a thing called a right map. And I'm going to show you what that is in a little while. And that brings us back to the construct map. And this is really where we do that important step of comparing what we got with what we expected. And again, it's a cycle. So let's go through that cycle in this case for ADM. Here's one of the construct maps for ADM. It's called Conceptions of Statistics, and it has 4 levels going from low to high, low sophistication to high sophistication, and the bottom of it is that a student can describe the qualities of the distribution informally. They might be able to say, well, it's got a hump in the middle, it's got long tails, something like that. The next step up is they can actually calculate statistics about that. So maybe they can tell us what the mean is, what's the median, what's the variance, what's the range. By the way, the math standards in many US states stop here. You calculate the statistics, you're done. Now, of course, that's not actually enough. As you know, those of you who are scientists will know, or study science, no, you actually want to be able to do things with the statistics. And so that's what the next few levels are. So this one is now, okay, we can have the statistics, but we want to think of them as measures of the qualities of a sample distribution. How do they help us understand this distribution? And so here's my image of what a learning progression might look like. Here's my sample science educator. I call him Joe. Actually after my good colleague Joe Krajcek, who is a science educator at the University of Michigan. And he has these thoughts about a learning progression, and they sort of, you know, they're vague thoughts, so I've illustrated them as clouds. They're complicated, but they do have an order. He wants them to get up to here like a good practicing scientist, but he knows that when students are starting, they're down the bottom here. They don't know much and it's not terribly well organised, but they're going to sort of get better and better as they go up. So that's sort of just a comic image of a learning progression. Now, on the other hand, these construct maps are very rigid things. No, they're not rigid, but they're very well defined. And so we think of them as maybe having a sort of a structure like this. And I'm going to use an icon. I'm going to create an icon out of that. So this is and don't try and read that, by the way. Those letters don't make any sense. I just want you to think of it as an idea. So I'm going to take this construct map and use an icon like this to illustrate what I mean. And then I'm going to try and talk about the relationship between the construct map and the learning progression. And what might that be? Well, here's one way we can think of it. That is, the constructs could sort of be like the latitude or the longitude of the learning progression. They could tell us where the kids are as they develop through these different levels. They simply go up in these different dimensions. That's one way we can think of it. a slightly different way to think of it might be like this. That is that, yes, still a four-dimensional profile, but that the dimensions start at different points as you become more sophisticated. The reason this is sort of interesting is that the way we look at it here, it looks like four continuous profiles, but it's actually, there's a discontinuity, there's a qualitative difference. So that when you're down below here, really you're only being measured by these two dimensions. As you go up, you start to be measured by these two dimensions, maybe these three dimensions, and right at the top, it's these two dimensions up here that become important. So here's a case where we have this sort of idea of continuous development, but in fact if we take a snapshot, a cross-sectional look at that, we will see important qualitative differences out of a quantitative sort of approach. There can be other sorts of images we could build. Here's a very extreme case. That's where the whole learning progression is somehow summarised by one construct map. I think that this is probably certainly not a good idea if you want to have diagnostic information, but it turns out it's basically what you're doing in PISA or something like that. If you can go and look at how PISA is developed, they will actually talk about the development of a thing called a described variable. And that's what it's doing. It's trying to impose one map over this whole complicated thing. And I'm not speaking against that, by the way, but we need to recognise its limitations. It's not going to be useful diagnostically. It is useful for telling whether a kid's down here or up here. That's the point of things like PISA. Other sorts of ones you could have that you would essentially create different variables within each of the levels of the learning progression. That's another thing you could do. And in fact, there are historical examples of this. For instance, if you do some work in Piagetian studies and you're looking at students going from different stages in Piagetian studies, from construct to formal operations, then essentially the different sets of items form different learning scales like this. Now there can be interesting relationships between these, and I actually did my dissertation on the relationship between scales that measure different stages of development. And it's sort of fun stuff if you like mathematical statistics. Other people are not so interested in it, but I think it's fun. You can also get complicated diagrams like this where it's not just that we describe different levels, but there are interesting interrelationships that are part of the structure of these dimensions. And in fact, this is the sort of way we ended up going in that ADM project. And I'll show you that in a minute. So remember the ADM project had these different aspects of what's going on. There's these posing questions, generating, selecting attributes, measuring, structuring, all these different things. Well, basically we created a set of dimensions that cover this whole range. And here is a list of the 7 dimensions we created. These first 6 are the dimensions of learning about data display and data modelling, and the final one down here is the thing you're measuring. And in this case, this was the theory of measurement, and this was about those activities. The activity I said, that you've got to measure the teacher's arm span or measure the height of a distant tree, and there you've got to know something about measurement, physical measurement that is, in order to do that. Of course, if you're studying the life cycle of a silkworm or something like that, then what you would need to know down here is theory of the lifestyle cycle of a silkworm. So these act on a particular piece of knowledge or particular area of knowledge. And I won't try and go into these because it's sort of a lot of detail, but there's 2 variables. I'll just mention them very quickly. These 2 dimensions here, one is about can you represent data and understand representations of data? And this is sort of knowing how to be strategic in using that. How can you interpret it in a meaningful way? This is the one we talked about, COS, conceptions of statistics. You've already looked at that in quite a lot of detail. Chance is measuring how much students understand the probability behind the spinners that they're using. This one here, it turns out, in terms of the biology of what's going on in the biological examples, is crucial. That is modelling variability. Understanding that normal populations have variability and that's crucial. That's the key to that there. And then, of course, on top of all of that, can the kids actually infer? Can they say, yeah, well, this is supporting such and such a hypothesis, or not supporting it? And this isn't formal, this is just middle school kids, so it's very informal. But in fact, we want kids to be able to use the fact that they've got probabilistic models about variability to answer scientific hypotheses. So that's the very quick summary of the 7 dimensions. And here's our picture of our 7 dimensions. The 7 dimensions go from here's theory of measurement, meta-representational competence, data displays, conception of statistics, chance, modelling variation, informal inference. And you can see that each of them is sort of put in this same series of levels as in the construct map I showed before. Here's the construct map for COS. Notice there's 1, 2, 3, 4. They're the 4 levels we saw earlier. But what we've done is tried to map out both the relativities between the levels of each dimension and also connections between them. And we've got a special little thing here, this little box here we call bootstrapping, because what we found was that even though we could pick up different levels of meta-representational competence and different levels of data display, when they actually learn them, they sort of tend to just go backwards and forwards here all the time. The relations amongst them was very complex, in other words. And then as we go on from COS, there's a very crucial level here of COS, as you'll notice, because you've got to be able to get to that 3rd level of COS. That's the one that I illustrated in order to really make this big jump for chance, modelling variation, informal inference. But then from then on, they go on, and at the top level is this testing hypotheses about scientific statements using informal inference. By examining the logic that the students were using and by examining the items, we also came up with these connections. These are very specific connections that basically, for instance, if there's an arrow from one point to another, it's saying you really can't deal with COS 3 in the context of measurement unless you're right at the top here. You can't really go on and get to the 3rd level of chance unless you're already at the 3rd level of COS and so on. So these are sort of prerequisite relations. They come from our experience as teachers. They come from our empirical work of looking at what kids get to these different levels. And they come from examining items in particular and student responses to items. So this is effectively a set of hypotheses. These arrows are hypotheses that we then test empirically. We're currently in the process of doing the testing on these. There's an awful lot of hypotheses embedded in this diagram, and we haven't got through them all yet. But in fact, we've mainly been looking so far at relationships between COS and chance and modelling variation, this sort of little core bit in here. And we're finding that some of what we have assumed is true and some of it isn't. We're very strongly hampered at the moment, though, by one of the things that happened is that this top level here is not very well understood by middle school students. So we're going to have to move up the school probably to grade 10 or grade 11 of our schools to really get kids working in this area. So this remains hypothetical because we can't really test it empirically with our current data. So this is an example of a very detailed learning progression. As you can see, there's a lot of information here that tells someone who understands what each of these levels means about what they need to know in order to succeed at that level and where they're going next. Each of these little rectangles here is not only a definition as in our construct maps, but is also a set of items that are available online, as well as examples of student responses. So teachers can actually go and look up in detail what it is that kids at this level say and do. And the same is true for every other level. So it ends up being a very dense resource for teachers about this whole area of knowledge. I'm now down to my last point, because this last thing is very simple in a sense. Because we've done so much work to get here. Remember, this is about classroom assessment. This is what's needed for classroom assessment. Now we come to the question, how do we design large-scale assessments if we've done all that? Well, let's start off. Well, one thing you can see, if you look, just the first thing you see in this diagram almost is that level there is really important. If you don't get there, then you don't get anywhere up here. So this is our first not point. We can choose this. We know this is really crucially important. So we better include these items in our large-scale assessment. What else should we include? Well, we can start to think of these guys up here are also very important. Not only are they cumulative in the sense that they're at the top, but they're also, each of them is very important for going on to informal inference. Notice the arrows. So because this is our final aim, we better know about these two levels here too. Equally, if we go down, then these levels down here are important. This whole area of bootstrapping this is actually confused. I mean, we've taken confusion and labelled it bootstrapping. We're not sure, but we know you better take some items out of there. But also, we better take some items out of the bottom and the top. And so what we get here is now a plan for sampling our large-scale assessment that's very simple. We've simply taken the most important points out of the diagnostic map, the progress map. And this is what we put in our large-scale assessment. So this solves that problem that we talked about. Well, do we have to have items for every bit, every standard? Every one of these is at least one standard, if not two or three. So we've eliminated the need to really test any of these standards or any of these standards. We really only need to test these ones at the summative level. It'll do just as well. In fact, it's the crucial things they better know. So that's that solution. We've solved that problem. Of course, as I said, getting to here is a lot of work. So we've solved the problem given we do a lot of work. That's the caveat on it. So let's just summarise then. The large-scale test becomes a derived measure. It becomes based on the sampling design of the levels across the 7 constructs. We can control reliability, which is one of the major things in standardised tests. You want to have high reliability. Well, we just have lighter or heavier sampling. And because we've chosen so few standards, that's not really a problem. You can also post hoc develop I put a construct map in quotation marks. This is the thing that PISA does. It's called a defined variable. Now the trick about PISA is it defines it without doing all of this work. It gets a set of experts to sit around a table and tell us what they think these things are. Now they have no empirical information about that. They have their life of expertise. And they may be wrong, they may be right. I don't know. But indeed PISA's already done something like that, and they then go backwards from these to a thing called a described variable. And it's like a construct map. And we can also, of course, use other learning progressions with that. We would, in this case, this would be in the maths curriculum, and obviously there are other bits of maths we'd want to include. Get to my conclusion. So we could see learning progressions, they can provide a way to deal with classroom assessments and large-scale assessments and the coordination between the two, the necessary coordination. So they help us get over that problem of how we don't want the large-scale assessments forcing the classroom assessments in a particular direction. We need to establish a relationship between them. We need to design this outcome progression to allow this to occur. And these construct maps are used to tile the learning progression. They sort of fill up the learning progression. Let me show you what I mean by tile. Remember, the way I use that word tile, it's sort of like, you know, going back to sort of like this, I guess, that the learning progression in the minds of the science educators is sort of a big fuzzy thing, but it's got important ideas in it, and essentially we want to take the essential structure out of it. We want to see the tile of that. Now there are challenges involved in this. Well, first one is we need to develop those learning progressions. We need to have them, and they're just not there. The textbooks that we have are written the wrong way. They're written for the structure of knowledge. They need to be written for the structure of learning. There's going to be this sort of debate that occurs, and it's a political/curriculum debate. What's important? You know, I'm a nanoscientist. I insist nanoscience must be in there. Well, you've got to have an answer for people like that. Maybe nanoscience should be in there. I'm not saying it shouldn't, but you can't have the situation where everyone comes and brings their piece of knowledge and says it has to be in there. We need to develop assessments. We need to go beyond that. We actually, in order to develop the learning progressions, we need to develop assessments. They're sort of the two things go together, as I've been illustrating in the BEAR assessment system. We need new measurement approaches for those links. It turns out that those links are somewhat different from the things that we often use. I'm sure, Roman, you were saying, well, are they structural equation models? Well, they're not. And they're more complicated than structural equation models. And here's the reason, that it's because these links we're talking about, a structural equation model would posit links between this dimension and that dimension, but this is a link between that level of that dimension and that level of that dimension. So there are things that are, if those of you have heard of structural equation models, these things are more complicated than them. And finally, if we're going to create these large-scale assessments, we need to rethink the idea of the blueprint. The blueprint needs to be something like this, where we know the relationship that we want them to have in the classroom, and then we pick out the things we want in the large-scale assessment. And we can't just go straight to the large-scale assessment. There's some interesting, we can push out from this. There are new variables to measure. One of the ones, an example I've been working on recently, and I'll talk about in the workshop, is, for example, building knowledge through social networks. This is an idea of knowledge that didn't even exist 10 years ago because we didn't really have those social networks, at least not information science-based one. These sort of new and interesting things to measure will cause problems because it's just, when do we have time to test all of that? So we're going to have to find ways to make room by doubling up, by, for instance, measuring content and process together. Can we measure the processes of science as well as the content of science? And that is, in fact, a challenge that many people are working on at the moment in the United States. But there are new technological developments. So one way, for instance, that we've been measuring this knowledge through social networks is by tracking students' network moves. What do they do in the network? So we're not just asking them to solve problems with respect to social networks. We actually let them do it and then track what they do. And so technological developments can give us more information, it turns out. You've got to think about them the right way. And again, I'll talk about this in the workshop. One of the interesting things I think about this is that curricula, when you express them as a learning progression, actually become testable hypotheses. We can test whether the curriculum works or not. We can't just, if you think of most curricula, someone says, this is a good idea, I'm going to create a curriculum that looks this way, and they write a textbook or something goes with it, and then people use it. And maybe at the most what they do is they run a horse race between that textbook and this textbook. That's the most it's ever done. Well, the problem with that is that actually each curriculum is full of thousands of decisions. And really we need to be able to unpack some of the most critical of those decisions. And really a learning progression allows us to go beyond that sort of horse race comparison. It might lead to new ways to think of structuring curricula. If we have an image of what a curriculum looks like that's hypothesizable and testable, then we can be creative about that. And we can carry out all sorts of research on learning progressions. But also, of course, anytime we want to carry out that investigative research, we're back in the game of creating assessments, and that's where I come in. So, as I mentioned, there's that set of references to these that I've made reference to during the talk. So if you get hold of the slides, you'll also be able to get hold of them. I'm happy to, if you guys want to get in touch with me, to send me an email, and I can send those things to you. And I will write my email address just down here. Do we have questions? The key here is there's a breakdown in the classical way of doing this. And the classical way of doing this, you treat this as a list. You say, right, they're all the standards. Just for the moment, imagine there's one standard per box. In fact, there's several more, usually 2 or 3. But we just sample that. And we just make sure that there's 1 item for every box or 2 items for every box and so on. That's the standard way of doing it. And it makes sense, right? It's legitimate. That's the things we say we're going to teach. This is what we're going to test. The problem is that, as I've said, you can't actually use that diagnostically. You can't go back and say, the person got 73 out of 100, therefore that's a certain point on the scale. Doesn't mean anything because it's too complicated to go from 1 dimension back to this many to 7 dimensions in this case. You can't go backwards. If you structure it this way, notice we still cover, I mean, effectively, in terms of if the variable goes from low to high here, then we've covered every part of the variable, notice, from low to high. There are items in every one of them, so we're going to still be able to get a number for every kid from low to high. But in fact, what we'll do is we'll have more items for each of these Enough, in fact, to say, well, it's not just that we know that the kid's about here, but we know that they can do this. And so there will actually be diagnostic information available. So this, by ignoring this, I mean, we say, we know from our studies that if you know these, you tend to know these. We use that empirical fact, and we create a more meaningful summary. It's still only a summary. That's one thing. So that's the answer at the level of the summative test. The important thing is, though, that when this goes back out into the classroom, the teacher in the classroom is equipped with this, but they're working on all of these at any one time. So they will be giving their classroom tests, will in fact be at the greater level of detail. And the two will be connectable. So we'll be able to say, well, if we get a certain point here on this one, we can connect not only to the fact that they're learning or able to do this level of cos, they will also be able to predict how they'll do on these other dimensions here. Now, it certainly involves an empirical prediction, but that's what we do with a standardised test anyway. So it does all the things that a standardised test do, and it does some more, it gives you some more information, but it also doesn't involve this pressure of pressing in on the curriculum and making teachers teach in a very particular way. So that's sort of the answer to that. It is a complicated thing. I mean, it's not, you know, you'd like that the simple logic worked all the time, but in fact, we've tried out the simple logic and it's doing a bad thing. So we know it's not the right thing.
Do you believe this model is exactly the same in every domain? For example, statistics, spacecraft, or I don't know, language learning. I don't know. Whatever domain.
Will it work in every domain? I think it's an excellent question. I tend to work in maths and science just because I sort of like those domains. So I've been mainly come out of that area. I have been working with people who are teaching adolescents to read. So this is basically kids who didn't learn to read when they should have, and then all got to adolescence. And we've managed to turn reading this way too. Now, people who teach reading, a lot of them don't like this sort of stuff because they like to think of it as these sort of broad, fuzzy continuum. You know, they like to think of the structure of their domain as being like that. You know, it's broad and fuzzy, and they don't want to see someone putting a map on it like that. They're ideologically opposed to that. What I found is you can do it though if you try, and so I would say the domains I've tried to work in, which have been mainly maths and science, some work in reading, some work in 21st century skills, specifically the networking and the collaborative problem solving. We've been able to do this. We've also done it for other areas like undergraduate physics and undergraduate chemistry. We've worked in those areas, and it seems to work quite well in the areas we've taken on. I have not done it in every area though. There could well be, you know, there may be things that are, you know, it's very intuitive and it's hard to express these sort of more sort of fine-grained skills that grow up to be others, then it might make it hard. It certainly could be true. Thank you for coming.